Now we understand a little bit better how the rainbow functions. But as you might have noticed, we've actually only explained this part of a rainbow effect, so the primary rainbow. But if you have particularly good rainbowish weather, then you can see other effects. For example, a secondary rainbow, like it is seen here, where the colors are reverted. So rather than red being outside, it's now on the inside. And you can even see sometimes what is called supernumerary rainbows. So you can see another sort of red, green, blue inside, and in very rare occasions, even like twice the same effect. And there's also an effect that you see here, which is that there's a brighter area in here of brighter light and dark light between the two rainbows. So all of these effects can, of course, also be explained. This is the effect by one reflection. The secondary bow is you get by looking at two internal reflections of water droplets. And the supernumerary rainbows are explained by diffraction effects. And that is also why the quality of the rainbow depends a little bit on the weather conditions, because it depends on the size of the droplets. If the droplets are too small, then you have to consider not only ray optics, but also wave optics effects such as diffraction, and they can actually ultimately give rise to the supernumerary rainbows. So here's a little more detail on the rainbow. So these figures on the left show you what happens with two reflections. So the light enters here and you get a similar extremal effect, this time only the other way around, such that the red is inside as an extremal position, in this case at 50.4 degrees, whereas the blue light would be extremal at 53.5 degrees. So that's why it is the other way around. Okay, so enough about rainbows. So what I've done here is there's a table of refractive indices of different media. So this is sort of good to know. So in the future, when you get a little bit experience working with actual optics, you will at least remember a few of them. I would say the most important one is that vacuum, of course, has a refractive index of 1, which means that you have, for example, just the normal speed of light that is typically referred to as the speed of light in vacuum. So the refractive index doesn't change from there, of course. Then air has pretty much the same refractive index. So only in the 4th digit after the comma you get a change. However, if you have something like water, you get a pretty massive change. Like you see that the wavelengths get actually shortened by 1.3 times. So the effect of the refractive index is that it shortens the wavelength. So you divide the vacuum wavelength by n to get the wavelengths in the medium. So a factor 1.33 in water. In typical glass, it would be 1.51 BK7 glass or 1.52. And then you have other glasses. That is, of course, the whole art of constructing objectives and so on, is use different glasses to get ideally achromatic performance in the end. And diamond, for example, has a very high refractive index. But many media, for example, if you go to the IR, you get typically quite high refractive indices, for example, of silicon. So the rule of thumb is whenever you get close to an absorption possibility of the medium, you get relatively high refractive indices. So as you note here, this table is given for 20 degrees Celsius and a particular wavelength. Why? Well, because all of these depend on the wavelengths and the temperature. So that is an effect called dispersion, that the refractive index, the index of refraction, depends on the wavelength. So remember dispersion. So let's look a little bit more in detail on the effects of reflection and refraction. We start with reflection, and of course you know that the law of reflection says that the input angle towards the normal is equal to the exit angle. And you see that here, if we stand in front of a mirror hanging at the wall as shown here with a particular size, for example, the light from the tip of our shoe reaches the mirror, gets reflected, and then finally reaches our eye. However, if we look at that, we are not aware of the mirror, our brain thinks that the light comes from this line, and it basically traces the line back in this direction, and we get what is called a virtual image here, standing there. And if the mirror is big enough, we can just about see our own feet here again. Of course, with the eyes, we would basically look ourselves into the eyes and then also perceive that at a particular distance here. So, how about curved mirrors now? What this is, it indicates a curved reflective surface. So in this case, a concave mirror. So now we have an object somewhere, and we are looking where an image will be formed. And in this situation, if the object stands inside this curved mirror, relatively close to it, you see that the laws of reflection would predict that a ray this way, input angles, output angle to the normal goes this direction. And here, for example, if the ray that goes from the top of the object to that sort of point where the optic axis hits the mirror, then it would just leave at the same angle outside. And so you see that these rays never cross, therefore we do not get a real image of the object. However, if we then would place our eye here, we would perceive an image here. It would look to us as if there's a focused enlarged object here. So we get an upright virtual image of the object here. Note that this curve here has a focus position that is here. What does that mean? That means that a parallel rays here will actually focus at this point here, which is half the distance to its actually radius. So if we had this position is basically the radius of the curve of this circular approximated curve here. And if you had a ray that goes from here towards the mirror, it would always return to itself. So that is why it's called the center of curvature here. So that's an interesting effect, that curved mirrors always have sort of a center of curvature and a focus, and they are different in distance by a factor of 2. So if we now move the object to a different position, we actually see that this graph here doesn't show an object. What is the reason? Because if the object is just at the focus position, well, it would be infinitely big at infinite distance. You see that these are two parallel rays now, and you see that the rays never cross, neither on this side to form a real image, nor on this side to form a virtual image. So that is an image at infinite distance. Is that a real problem? Not really, because if we place our eyes here, we would nicely see such an image at infinite distance, because for all practical purposes, if we look at the horizon or the clouds or something like that, that is infinitely away for practical purposes for the eye. So we don't have a problem seeing these images at infinite distance, but how big is it? Well, it's infinitely big because it's infinitely far away, right? So that doesn't make sense. And for this, the reason in these situations, usually you refer to a particular distance to measure the size there when you talk about magnification. And so this is basically a particular distance that is sort of close to the close point of the eye. So I don't remember exactly that distance, but it's in the range. It's, I think, less than a meter for sure. So if we move the object further away, you see that we now get a real image that is upside down. So an inverted real image, and it's magnified here. And then we move the object even further away. At 2f, we just get with a 1 magnification an inverted image. That means that the light rays here are crossing here and they form an image. We could actually put a screen here, and on the screen we would see a nice image of a, for example, self-luminous object. If we move it even further away, then we get a demagnified image that is real and inverted, like you see here. So of course there's not only concave mirrors, but there's also convex mirrors, as you see here. So in this case, we would get a demagnified virtual image on the other side of the mirror. And you can see a nice example of that. Here is such a curved mirror, which gives us a nice overview around the corner, so to say, if there's something. So you see these sort of mirrors often in traffic as traffic mirrors to basically indicate what's going on in a bigger field of view. Well, I want to also mention what is called the parabolic mirror, because that is in a way an ideal system to focus from infinity to the focus point. So imagine that we have light from infinite away. Stars could be such an example, and they would perfectly focus here to the focal point. Well, where do we need this? For example, in a satellite dish, we want to really capture the signal of the satellite with maximum power, and we want to therefore concentrate it as good as possible on our detector, and that's why such a parabolic form is used. However, in optics, you have to be a little bit careful, because this looks all fine for this particular situation. However, if we had now an infinite distance at some angle, we would find that the focus is not quite as good anymore. So we have only a certain sort of field of view, in other words, a certain range of angles where the image quality is acceptable. Here you see that whole thing rendered in 3D, and you can see and appreciate that all parallel rays on the whole surface of the mirror would really focus in this focus. One other way of looking at that is that they also constructively interfere here. When we come to wave optics later, we will follow what is called Fermat's principle, which means that we have to ensure that not only do they all meet in the same point, but they actually have the same path length. So if you add it up mathematically, which is sort of a fun exercise to do, the blue lines for each of these paths, you would find that they are the same length, and that of course defines the shape of the parabola that you see here. So what about reflection when the surface is not that well defined? And you have here an example of a rough surface, and what you see is that of course we get reflected rays that go in all directions. That depends on where they locally hit the surface normal, how it is oriented. And depending on the roughness, you get a different distribution of scattered light. So you call this scattered light from the surface. And under certain conditions, this distribution follows what is called Lambert's cosine law. So you can basically say that the power here follows a particular distribution, which is called Lambert's cosine law. Of course, you do have also a specular reflection, which is sort of, if you take the surface normal on a coarse coordinate, the specular reflection would follow the normal laws of reflection at such a surface. However, the micro orientations are different, and that give rise to this what is called scattered light or diffuse reflection. As we've now talked a little bit about mirrors, I want you to think about this question. Why does a mirror reverse left and right, however it does not reverse the up and down direction? So what is so special about left and right, but not at up and down? If you look at a mirror and you raise your right hand, the person in the mirror clearly raises his or her left hand, whereas you've never seen in a mirror yourself upside down, at least not with a single reflection. So why does the mirror reverse left and right, but not up and down? Think about it and then tell me the answer.